2, 1, let's have fun. Alright, here we go. We're going to get 1 to 1. We're going to get on to. We're going to have a good time. Okay, so we're now going to talk about 5.4 and 5.5, where we'll talk about certain types of linear mappings. The fancy word, isomorphism, is going to show up. Okay, so before we get to that, let's discuss what 1-to-1 and onto mean. So, hopefully, these are familiar, and you remember them from 201, your intro proofs course. Alright, so remember, a function is called 1-to-1 if outputs line up. That means the inputs had to line up. Now note, if inputs are the same, outputs are the same, but the reverse is not necessarily true. Right, so for example, x squared is not a 1-to-1 function because if you feed in 1 or minus 1, you'll get the same number, 1. But x cubed is 1-to-1, and if you remember, a way of thinking about that is that it passes the horizontal line test. Alright. And the analogous thing here now, the other thing, 1-onto, if given something out of the codomain, there is an input that hits it. Equivalently, the range of x is y. Now, note, x squared is not onto because there's nothing that hits -1, but if I change its codomain to the non-negative real numbers, now that is onto because I can feed it square roots. And if you square a square root, you get back what's on the inside. Nice. So this specifically highlights that every function can be viewed as an onto one to its range. And again, like I've said, when it comes to changing the codomain of a function, some people will take the stance that this function right here is different from this one because their codomains are different, but I am not a fan of that. These are the same function, they just have different codomains. That's fine. You can have different codomains. But anyway. So that's why when we kind of do calculus, we kind of only care about 1-to-1. And in fact, usually only care about 1-to-1 because basically you've got a function, you can change its codomain. And no, 1-to-1 does not care about codomain because it's asking about output of functions, and that's something that's happening only in the range. But anyway, so our first task is to discuss that 1-to-1 and onto linear functions are very nicely behaved. Specifically, the 1-to-1 ones have an amazing theorem associated with them. This one right here. Linear functions are 1-to-1 precisely when their kernel is trivial. And this is an amazing result. I really want to stress, this is big time good stuff. All right. Legit, not joking, this is a very useful and important result. Okay, so let's prove it. And in fact, this is a neat proof. This is one of my all-time favorite proofs. All right, so suppose that you're 1-to-1. Note that the kernel is always non-empty. It's a subspace, so it's always got the 0 vector. I claim it's trivial if your mapping's 1-to-1. Pick something out of the kernel. Aha! Your outputs are the same. That means your inputs are the same. Boom, kernel is trivial. Boom, 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 nailed it. And note that we did use the linearity here, kind of subtly. We used it by pointing out that the kernel of f is actually a subspace. So if you're kind of pausing it for a moment going like, wait, did we actually use linearity? We did. We snuck it in here with the fact that the kernel is a subspace, guaranteeing that this set is non-empty and has the 0 element in it. So note, you could modify it if you didn't want linearity, if you're just like, well, you just have the 0 element in there, but we use the linearity there. Now let's more outright use the linearity. It's an if and only if, so suppose that the kernel is trivial. Pick two things whose outputs line up. Linearity allows me to look at the difference and break up over the difference, and hey, that has a output of 0, that must be in the kernel, and ha-ha, they have to be the same. Boom, you're 1-to-1. Nice. So I connected a set theoretic idea, right, this idea of our functions behaving, to an algebraic idea. So I've connected algebra to set theoretic tools. I'm clapping, because that's an amazing thing, right? These sorts of connections here, you always want to kind of make them because they will make your life a lot easier. All right. Okay, so we got a characterization of one-to-one mappings, linear mappings, in terms of a linear algebraic ingredient, the kernel. We can do the same thing for onto mappings. A mapping is onto precisely when the dimension of its range and the dimension of its codomain are the same. So note here is kind of like a different version of the rank nullity, right? Before where we were like the domain is finite dimensional. Here the range is finite dimensional. Okay, so you're onto precisely when the dimensions line up. So let's do that proof. Suppose you're onto. Well, then you just equal the set, so the dimensions are the same. Okay, that one isn't exciting, but it is. Now note, I'm allowed to talk about the dimension of f of v because I'm linear, so f of v is a subspace, so I am using linearity here, right? And again, when we're proving stuff, always check to make sure you're using all the hypotheses. All right. Conversely, suppose that the dimension of the range is the dimension of the codomain. So if the dimension of the vector space W was 0, that would mean that the dimension of the range was 0, so they're both trivial, which means you got to be onto. Okay, so let's take over the non-trivial case. All right, so take a basis for the range then. Note that that set also has to be a basis for W. W is a n-dimensional space. I have n linearly independent things. It must be a basis. If it didn't span the set, I can make it bigger, which contradicts that the dimension is n. So then given anything out of W, it has to line up with those. But these V1 and Vn's, those are in the range, which means I can find inputs to line up with it using the linearity. Then I get that y lined up with f for some input. Boom, it is onto. Nice. Slick proof. Cool. All right, so there we go. Onto linear mappings now can also be characterized in terms of linear algebraic facts. Very beautiful, very nice, very useful, as we're going to see. Because now I can also tell you something really neat. If you've got finite dimensional vector spaces and the dimension of V is the dimension of W, one-to-one and onto are equivalent. Note, in general, this never really happens, but in the case of finite dimensional vector spaces, this is true. This is actually mind-blowing that this is true, and this is incredible consequences. But all right, let's see it. Suppose you're one-to-one. That means your kernel is trivial. So that means your dimension has a triviality to it. It is the zero number, zero vector is what I was going to say, zero number. Hey, rank nullity, boom. The dimension of W has to be the dimension of the range of V. Boom, it's onto, as we just proved. Nice. Rank nullity. Hey, I told you, it's fundamental. Here we see. And in fact, we're going to use it multiple times today. All right, now that we got its onto, let's go backwards. Suppose you're onto. Then rank nullity means the dimension of the kernel space has to be 0, which means it's trivial, which means it's one-to-one. Boom, 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 boom. Cool theorem. Cool proof. I love this proof. This one's cool. Now, it's worth noting that we did this under the assumption of finite dimensional. This is not true anymore in the infinite dimensional case. This is, like, big time not true. And the fact that it's not true has a lot of weird consequences in that case. There are some replacement theorems. It's worth noting that rank nullity doesn't exactly have an infinite dimensional analog. There's some results that you can kind of go where, like, kind of rank nullity, but not really. Maybe I'll talk about those. I don't know. Now that I've proven this, I want to point out that you already knew this result, but you knew it in terms of matrices. If I take an n by n matrix, I can create that linear transformation right there. Note that it's one-to-one precisely when the homogeneous equation has a trivial solution, because one-to-one means the kernel is trivial, and as we discussed, the kernel of that linear transformation is the set of homogeneous solutions. Likewise, it's onto precisely when the matrix equation can always be solved. right? Because the range of that linear transformation is the set of all things whose matrix equation is solvable. And for matrices, we already know these facts are equivalent. If your homogeneous solution is trivial, every matrix equation can be solved then, because it's all related to the fact that the matrix is invertible. Now, there's something about being one-to-one and onto that is related to invertibility. Ooh, and you might have an exciting problem talking about the invertibility that's going on here. So recall now that a function is called invertible, also known as formally invertible, if there is an inverse function, meaning that the composition of the functions gives you the identity function, or more precisely written like this. So this is usually referred to as formally invertible because talking about a function being invertible, depending on the context, could have multiple interpretations. But when you want to be really precise, you will call this formally invertible. The function f inverse there is called the formal inverse then, or just the inverse if the context is clear. The notation is always f to the negative 1. If you need f to the negative 1 to mean something else, you usually do something else. Like 1 over f or negative f, when you need inverse in terms of algebraic operations. Anyway, so as I just said, invertibility is precisely the situation where you're both one-to-one and onto. So that was something that you hopefully saw and proved in 201, your proofs class. Now, note that if you're invertible, your inverse is also invertible, where its inverse is just itself. So here the power to the negative 1 is supposed to be making you think negative 1 times negative 1, giving you positive 1. Now, given invertible functions, their composition is invertible, where their inverse behaves the way you want it to. So this is just hopefully things that you remember from proofs and did yourself. Now, as we noted, I'm of the stance that every function can be viewed as an onto one. So that means invertibility really is just detecting if you're one-to-one or not. Right, which is why in calculus, when we talk about invertible functions, functions having an inverse, you only ever talk about the horizontal line test. Nice. Alright, so as we just discussed, for finite dimensional vector spaces, one-to-one and onto are equivalent, meaning that getting an inverse of your linear mapping boils down to just detecting one-to-one. Now, here is the other word we talked for today, isomorphism. So a linear mapping is called an isomorphism if it's one-to-one and onto. Equivalently if it's formally invertible. And the idea of a linear isomorphism, let's think about what it is saying. It's saying that as sets, V and W are the same, because there's a bijection, so everything in V lines up to exactly one thing in W. And since it's linear, that means the algebraic operations of V carry over to the algebraic operations of W. So, in other words, a linear isomorphism is saying that V and W are basically the same set, even if they are presenting themselves differently. Right? So, isomorphism, same morphism, morphism meaning the same object in a sense. And yeah, so if you haven't encountered the word isomorphism before, here you go. My favorite use of the word isomorphism happened when I was at a conference once. The conference center we were at had other events going on, so there was a math conference. There was also an Elvis impersonation conference going on for one reason or another. And so we left the talk, and Elvis was doing his Elvis thing. And he was a good Elvis impersonator, because his gimmick was that he was the ghost of Elvis in corporeal form. So he was talking about, like, I'm going to now sing a song back in when I was alive. So he had a good gimmick. That was a good Elvis impersonator. So we stopped and watched him. And while that was happening, my friend Lausch Molnar popped up behind me and he goes, "Hey, Chris, that's not Elvis, but that's isomorphic to Elvis." And I laughed very hard and audibly at that line. And I think I'm the only human being in the world who's ever laughed at the phrase isomorphic to Elvis. So, yeah. Anyway. So, here's the big fact about linear isomorphisms. So you're linear, and if you're isomorphic, that means we've got the inverse function f to the negative 1. That itself has to be linear. So if you're linear and you've got access to your inverse function is actually linear. Nice. And let's do that proof. Okay. So note V F inverse, its domain is W, right? Z and W come out of the codomain here, right? Because F inverse, its domain is the codomain for F. So I want to prove that F inverse of alpha Z plus W times beta is going to behave correctly. So how am I going to pull that off? Well, we're going to use the linearity of F. So note that if I do F of F inverse of some input, it will undo it. Apply that rule twice. Hey, F is linear, which means that it respects scaling and adding. F is equal to F. They cancel, and boom. There you go. That proof's really neat. Note we used everything. We used the fact that F is linear. We used that right here. And we used F inverse's properties twice. Right? We used it right here, and then we implicitly used it here again, where since F is invertible, it's 1-to-1, which means we can undo the F's on both sides. So, nice. We have truly used all of our hypotheses here. Pretty cool. All right, so if you've got a linear isomorphism, the inverse function itself is linear. And equipped with that, we can now discuss the following. Two vector spaces are said to be isomorphic if you can construct an isomorphism from one to the other. So it turns out that this satisfies three conditions. So specifically, if V is isomorphic to W, that is actually an equivalence relation in disguise. Now, it's specifically an equivalence relation, not on a set, but rather on something bigger, which is called a class, and some category theory nonsense now, but this is an important result. Now, note, as a consequence of this, when I say two vector spaces are isomorphic, point B here lets me get away with that phrase, because really, I want to say V is isomorphic to W, because domain and codomain, I want to make that clear. But as I said, here, it doesn't matter. You can swap the ordering. Okay, so if I want to prove that a vector space is isomorphic to another one, I want to construct an isomorphism. So for the vector space to itself, just take the identity mapping. That is obviously invertible. With itself, it's its inverse, and it's very clearly linear. So there you go. Isomorphic. Done. All right, now let's say I know that V is isomorphic to W. That means I have access to an isomorphism, and as I just proved, its inverse is both linear and invertible, so it's an isomorphism. It is an isomorphism. It's an isomorphism. Getting a little mush mouth, let me tell you. All right, so boom, W is isomorphic to V. Oh, hey, exactly what I just said. All right, well, now let's say you've got two isomorphisms. As we discussed, the composition of invertible things is invertible, and as we proved last week, the composition of linear things is linear. So, boom, isomorphism. Nice. And so now when we talk about isomorphic vector spaces, since it's an equivalence relation, we're allowed to basically swap order and transitivity my way wherever I want. All right, so what are we going to finish up with? So as we discussed, finite dimensional vector spaces are basically Rn, and now we're going to make that crystal clear by proving that they're isomorphic. Oh, hey, exactly what I just said. So if you've got a positive integer and a vector space with dimension n, it's Rn in disguise. They're isomorphic. They might be presenting themselves differently. Like, for example, V might be all of the polynomials of degree less than or equal to n minus 1, but they are isomorphic. So take a basis for B. As we discussed, if you've got a basis, you can create a linear function that maps those basis elements wherever you want. I'm going to send them to the standard basis, obviously. So, what do I need to prove? I just need to prove that it's invertible. Then they're isomorphic. Okay, so first I'll verify the kernel is trivial. So if we pick something out of the kernel, I've got a basis for V, then it's a linear combo of those things. Well, F is linear, so feed it into it, and oh hey, you get the standard basis vector, scales up and adds the 0 vector, so all those scalars must be 0, so V itself has to be 0. Kernel's trivial, boom, we've got F is 1 to 1. Alright. Now, let's show that we're onto, and we're going to prove this one directly. We're actually not going to show that the, another way of dealing with this would be to prove that it's, there's actually a couple of things. We actually could use rank nullity right now if you wanted to, but I'm going to just prove it directly. So, specifically, take anything out of V, well, then it's a linear combo of the standard basis vectors. Well, then, take those scalars, scale up V, add them up, feed it into F, and boom, there you go, it's on to. Nice, so, there we go. Every finite dimensional vector space is Rn in the skies for positive integers. Okay, now equipped with this, we can prove the big result for today. For finite dimensional vector spaces, if the dimensions line up, then you have to be isomorphic. Shouldn't be too surprising. Now, I do want to point out that even though I talked about before, we proved these things for finite dimensional vector spaces, and then noted that for infinite dimensional spaces, these kind of falls apart. I do want to note that for the infinite dimensional case, this result is actually still true. It is much more of a pain to prove, though. In the infinite dimensional case, the dimension right isn't a finite number anymore. So creating the linear isomorphism is a lot more of a pain in the ass. But this proof here is actually super easy because we've got the rank nullity theorem. So let's do it. So let's say your dimensions are the same. So note that if they were 0, then the vector spaces are trivial, which means that they're trivially isomorphic. So we don't need to consider that case. So let's say it's a positive integer. Well, that means V is isomorphic to Rn, and W is isomorphic to Rn. And by transitivity and of the equivalenceness of isomorphicity, those are all fake words, right? As we already proved, if you're isomorphic, you can use the transitivity of that relationship to then get that V and W have to be isomorphic. Right, V is isomorphic to Rn, Rn is isomorphic to itself, and Rn is isomorphic to W, so V has to be isomorphic to W. Alright, now let's go reverse. Suppose you're isomorphic. That means there is an isomorphism, and rank nullity saves the day. Because if you're isomorphic, that means you're 1 to 1 and onto, which means the dimension of your kernel is trivial, and the dimension of your range is the whole space. So the dimension of V is the dimension of W. Boom! Rank nullity. Alright, nice. So as I said, in the finite dimensional case, this part is easy. For the infinite dimensional case, this theorem is still true, but this direction is much more difficult to prove. Actually verifying the dimensions are the same is much more difficult, and given the dimensions are the same, creating the linear isomorphism is a much bigger pain in the ass. But for finite dimensions, nice and clean. Alright, and hey, there we go. Nice. Alright, well, we've now proven quite a bit of stuff, so what's next? So next we're going to revisit eigenvalues, and we're going to connect eigenvalues to linear transformations. Nice. That's going to be pretty interesting. Alright, that's it for today. I'll see you next time.